We're finally going to look at the wave equation, which is a hyperbolic equation. It involves a second derivative with respect to time, as well as a second derivative with respect to x, in this sort of two-dimensional version of the wave equation. We have those terms that prescribe the value of our field variable u along x and t. If we are looking at this one-dimensional domain, then we need two boundary conditions because we have two temporal spatial derivatives. So those need to be prescribed. In this case, they are being prescribed by the functions g1 and g2 of t, completely at all times on the left and the right-hand side of our boundary. And we also need two initial conditions because we have a second-order derivative in our governing equation, and that's typically done by prescribing the value of the field variable at time equals 0 with some function u sub 0 of x, and prescribing the value of the velocity at time equals 0, which is equivalent to prescribing the value of the temporal derivative of u with respect to time at time equals 0 with a given function v sub 0 of x. Given those four conditions for functions g1, g2, u0, v0, our goal is to determine the value of u at all times and all locations on the interior of the space-time domain. So where does this problem come about? Since this has some affinity more affinity to structural engineering, which is my field, I'm going to give you a derivation of this PDE. If we're looking at a one-dimensional rod, for example, with an axial stiffness given to us by the product of the Young's modulus E and the cross-sectional area of our rod A, and density denoted by rho, what we're going to do is we're going to take a look at a small chunk of our rod that has a length of L, and this small chunk I've marked it with delta x. So I'm going to first take a look at the relationship between the strain that this little chunk undergoes and the displacement field that causes that straining. So if we're looking at the deformed shape of our little green segment, the left-hand side of our segment is going to displace along the x direction by a magnitude of u of x and t, and the right side will be displacing by a different amount in general, which is going to be marked by u of x plus delta x and t. And if these two values are different, that means that in particular if the right hand side has displaced more than the left hand side, the segment that we're looking at has stretched, it became longer, and if it's the opposite way, then it became shorter and got squeezed. If also those two values incidentally happen to be the same value, then it would be a rigid body motion. But whatever those possibilities are, we're going to look at them entirely, and through this we're going to describe our strain. So the strain is described by the new length divided by the original length. So that's a percent change in length. That's by definition what strain is. And we're going to first calculate that strain on this finite segment size delta x, which is going to be equal to the difference of the u's at the two ends normalized by the original length of our little segment. And we're then going to take the limit as delta x goes to 0, and thereby obtaining a pointwise description of strain and how it is related to the displacement field u, which is going to be our field variable in our governing equation ultimately. So what we have here is that the strain at any given point at any given time is equal to the partial derivative of the displacement field with respect to x, evaluated at whatever time and position we choose. Now let's take a look at the equilibrium equations we have on that same segment. Let's assume that we have some body forces, force per unit length, given to us by lowercase p of x and t. That would be an input to our problem. Then exposing the left and right hand sides, the internal forces on those locations, and denoting them with capital P's, we have a p of x and t pointing to the left, and a p of x plus delta x and t, which in general is going to have a different value than the one on the left side pointing to the right. And if we are looking at this dynamic problem, of course that's all the forces, external forces we have and internal forces we have. If there's a net unbalanced force between those two sets, the capital P and the little p, then that difference is going to create a D'Alembert force, an inertial force of magnitude mass times acceleration. And the mass is the mass density of our little segment rho multiplied by the cross-sectional area times the length of the segment, which is the volume, and u double dot is going to be the acceleration evaluated for this little piece. If we sum those two, if we sum all the forces with their correct signs, that's the equation we're going to have. This is the balance of linear momentum equation for our little segment. And again, I'm going to divide this equation by delta x, and then take the limit as delta x goes to 0, and that's going to be a pointwise description of balance of linear momentum along this one-dimensional rod. And that then is a partial of P, the internal force, internal axial force with respect to x, plus the body force multiplied by the cross-sectional area minus the inertial D'Alembert force we have. We're going to also assume the relationship between the internal force and the stress field within the cross-section is very simple, in that the internal stress field is uniform, such that when we multiply the internal stress sigma with the cross-sectional area, that gives us the p-value. If that's the case, then if we also assume that the cross-sectional area is prismatic, that it does not change along the x direction, we can take that outside that partial derivative that we see on the left-hand side and eliminate the constant a from the equation we have, and we're going to end up with this last equation. Partial of sigma with respect to x plus the body force p minus the inertial force is equal to 0 at all times, at all positions. Now our final task is going to be to relate the strain displacement equations to the stresses. That is going to be the constitutive law we have. Let's assume there's a linearly elastic relationship between the stress and strain, such that when I multiply the strain with the Young's modulus, it is going to give me the stress at that time, at that position. And from the strain displacement relationship, we can replace the strain epsilon with partial of u with respect to x, and we can take all of this and plug it into the balance of linear momentum equation that we have. If we also assume, again, the rod has a uniform Young's modulus, it's made of a single material along its length, then E is going to be constant with respect to the derivative of with respect to x. So we can pull it outside, and we will have the Young's modulus multiplying the second partial derivative of u with respect to x, plus the body force minus the inertial force equals to 0. If we rearrange this a little bit by dividing both sides of this equation by rho, carrying the p over rho term to the right-hand side, we're going to end up with this PDE. So the constant that we had before, that was multiplying the second derivative of u with respect to x, is indeed physically the Young's modulus divided by rho, which actually is equivalent to square of the wave speed in this rod, as it turns out. But more on that on a mechanics class. And the right-hand side is the driving function, which is entirely dependent upon the body force which we may have or may not, and as well the mass density of the system. So this is exactly the same equation we had in the previous slide. So we now know where it comes from. So let's try and go and solve this thing. Again, there are two distinct tracks that we can follow to solve it. We could do either the semi-discretization approach or the full discretization approach. The semi-discretization approach requires the discretization of one, in particular the spatial variable, which yields system of ODEs in time, and we can use an ODE solver to do that, so to obtain that solution. Full discretization requires you to approximate the derivatives along both x and t directions and discretize those two variables at the same time. And whether you choose an explicit or an implicit approximation for the derivatives, you're going to end up with a system of linear equations, which you can solve using a Gaussian elimination method or LU solver or anything like that. So let's talk about the explicit full discretization. Jump to that particular method right away. So let's discretize the x variable with n sub x points along the x direction with spacing hx, and discretize the time variable with n sub t points along the t direction, and obtain those discrete time instances, time slices, as well as the discrete x locations. So both variables are fully discretized, and the address of any point in the space-time continuum is given to us by x sub I, t sub k, and we can determine those locations and time instances by the simple algebraic relationships we have in the red boxes. Recall that our initial conditions were given to us, which prescribed the initial displacement at time equals 0 by a function u sub 0, and the initial velocity at time equals 0 u dot of x sub I is time equals 0 with v sub 0 of xi. So we have both the initial displacement and velocity at time equals 0. We also have our boundary values prescribed on the left and the right hand side of our domain at x equals 0 and x equals L at all times by functions g1 of t and g2 of t. So our goal is to basically fill in all the interior points. We're going to adopt a central difference formula for both derivatives we have along x and t directions. These are both second order accurate formulas. If we plug them into our governing equation, we're going to end up with this fully discrete system of equations. And these indices, as you notice, are going to involve evaluations of our field variable. In this particular case, the physical meaning of our field variable is the displacement field at time equals k plus 1, and time equals k minus 1. The boundary conditions will be used to fill in the values of the field variable, the displacement field, along x equals 0 and x equals L directions. And now we're going to have the slight inconvenience with respect to the initial conditions. It's very straightforward to impose the initial displacement condition, and we can just simply fill in the array u sub I at time equals 1 superscript 1 with the values of the function u sub 0 that is given to us. But what about the initial velocity? How are we going to satisfy that? Well, one way of doing that is to write this equation between the prescribed velocity and the discrete values of the field variable that we have at two time instances. One is a fictitious time or a previous time instance t equals 0, which doesn't even show up on our map here, and I'm going to draw it again, for you to see. And the other one involves the value of our u, which is unknown to us initially, at time equals t sub 2. And with this selection, the spacing between those two u's along the time direction is 2h sub t's. That's why we're dividing it by 2 ht's to get this approximation worked into our discrete system. Okay, so now we have these initial conditions and boundary conditions and the governing equations, the blue box. We're ready to fill in the blanks. And how do we do that? Well, this is our governing equations, and I pulled all the terms that I have that belong to time k and k minus 1 on the right hand side, along with our driving function, which happens to be something related to our body force, distributed body force along the length of the member, as we've described before. And with these values, we should be able to compute what the value of the displacement field is at time k plus 1. And we are going to certainly try and do this for k equals 1 first at all interior points. And if we look at that equation explicitly, if we look at that equation directly, what we have here is u of t, u superscript 2 is equal to all these values of u at time equals t1 and t0. And now this t0 time, the value of u at time equals t0 is problematic because we don't have access to that value. That value is not given to us. But luckily, our initial condition is going to tell us the value of that, of the displacement field at time equals 0, and this is the same equation that I wrote in the previous slide, which tells us u superscript 2 is equal to u superscript 0 at all positions plus 2 times ht of the times the given velocity function. So between these two equations, we should be able to eliminate this problematic term u superscript 0, and I can certainly do that by adding the two equations to each other and multiplying the result by a half, which gives me the u superscript 2 in terms of u superscript 1 and nothing else except the initial velocity and the driving force term. Since between the two terms the u superscript 0 had a plus and a minus value above, they have been eliminated. So now we can calculate u2. Once we've calculated u2, then it's pretty straightforward to calculate u3. Even though it will require u superscript 3 minus 1, that will be u superscript I'm sorry, u3 will require the calculation of u superscript 2 minus 1, which will be u1. That's already known to us. So after we have resolved this problem with the initial velocity issue, then we don't have that problem in any of the subsequent time steps, and we can march on as usual. Again, because this is an explicit method, and again, as I have shown you the equations, there's no need to solve a system of equations. It's just a matter of making the substitutions and marching the solution forward in time. However, again, the method is conditionally stable because we're using an explicit method here to approximate our second-order derivatives. Again, if you do the stability analysis, you'll see that if this ratio called gamma, which is a function of the characteristic value we had, which is the square of the wave speed, and the ratios of the time and spatial increments, if this particular ratio gamma is less than 1, then our errors are going to be bounded. In particular, the maximum error that is committed in any given time slab is going to be the upper bound for the maximum error in the next one, and the next one, and so on and so forth. This implies that the stability condition implies that you have to observe a certain ratio between the space increments and the time increments in your discretization. If you are able to satisfy this condition in the brown box, then your solution will be stable. Otherwise, you're going to end up with an unstable solution. Your errors are going to accumulate and blow up. The accuracy of the explicit full discretization we had for this wave equation is second order accurate in time and space, because we use those central difference formulas because they were second order accurate. Let's talk about quickly the MATLAB implementation of this technique. At the header we have our input. Our input consists of the characteristic value, which is the square of the wave speed, the driving function f, and the initial displacement field, initial velocity field, the boundary value functions g1 and g2 that describe the displacement at the left and the right hand side of our uniaxial rod at all times. So those are all prescribed functions. The user is supplying us with those handles, which we're going to call inside the subroutine to determine the values of our field variable there. The size of the domain is L. The ultimate time of interest is capital T, and the spacing the user chooses are NX and NT. After having those things, we do our initializations, which is essentially the discretization of the x and t variables. After that, we are going to first fill our function with the initial values, boundary values on the left and the right hand side, as well as the initial displacement field. Then we're going to do that little trick to eliminate the unknown displacement from time equals 0 past time, so that we can fill in completely the value of u at time equals t sub 2. After we do that, we can march forward in time, and every time we do this, we're just merely doing an evaluation. There's no solution of a system of algebraic equations or such to march in time. So it's pretty straightforward to march on from t equals t sub 2 all the way to the end of the time. We can see how our method works for a sample problem. Here the body force term is given to you by this weird function 2 times e superscript negative t sine of x. We are given an initial displacement. It's like a plucking of a string, if you will. If you imagined, visualized your one-dimensional wave propagation problem involving a guitar string, for example, this initial displacement field is essentially a half sine, which is like a plucked string. So that's the initial displacement. At time t equals to 0, and the boundary conditions we have on the left and the right hand side, where x equals 0 or x equals 1. Actually, I think there's a small typo here. I think the size of our domain is actually pi. At x equals pi, those values are fixed at all times. So it's indeed like a guitar string that is fixed on both ends. and given an initial displacement pattern that is like a sine function, half sine, and then I believe the initial velocity is prescribed to be 0, which is not written in here, but I think that's what it is. It's missing here. Please consult the textbook for this, but I think the initial velocity, although it's not written in here, is equal to 0. So if you solve this problem, you'll end up with this solution, which satisfies the two initial conditions and the boundary conditions at all times. And if we apply the forward Euler method, the fully discrete explicit method that we have described before, plug in these input values and functions into the MATLAB routine that we have described, and use 20 equally spaced points along the time and the spatial directions, you're going to end up with a solution that looks like this. So the error is bounded and small, and the solution was stable. And that concludes our discussion on partial differential equations.